Imagine peering into the earliest moments of the universe, a time when the first stars sparked to life and galaxies were only just beginning to form in the vast cosmic darkness. Now picture a telescope so powerful it can see the faint, stretched-out light from those ancient epochs, billions of years in the past. This is the promise of the James Webb Space Telescope, humanity's most ambitious eye on the cosmos. And just recently, it delivered a discovery that has astronomers buzzing with excitement and questions. 300 objects, shining brighter than anything we expected from the dawn of time. What are these cosmic beacons? Are they some of the first galaxies ever to exist? Or are they something altogether unexpected, signposts to a new understanding of the universe's infancy? The answers could force us to rewrite everything we know about how galaxies, and perhaps the universe itself, came to be. The story begins with a meticulous search led by scientists at the University of Missouri. Using Webb's advanced instruments, they set out to peer deeper into space and therefore further back in time than ever before. Their quarry, the faint, elusive signatures of the first galaxies hidden in the cosmic background. But instead of a handful of dim smudges, they found hundreds of points of light, each one brighter than theory suggested was possible so soon after the Big Bang. The James Webb Space Telescope is uniquely equipped for this kind of detective work. Its near-infrared camera and mid-infrared instrument are designed to hunt for light that has traveled across the vast gulfs of space and time. As the universe expands, the light from distant galaxies is stretched or redshifted, shifting it from the visible spectrum into the longer wavelengths of infrared. This means Webb isn't just looking for galaxies, it's searching for the ancient echoes of their light, transformed by billions of years of cosmic growth. Astronomers call this phenomenon redshift, and it's a crucial tool for measuring the distance, and thus the age, of galaxies. The higher the redshift, the further away the object, and the closer it is to the beginning of the universe. The galaxies identified in this study could be among the most distant ever found, existing at a time when the cosmos was just a fraction of its current age. But spotting potential galaxies from across the universe is only the first step. To separate true ancient galaxies from imposters, stars or other objects that might mimic their appearance, scientists rely on a clever technique known as the dropout method. In essence, researchers look for objects that appear in images taken at redder, longer wavelengths, but disappear or drop out in bluer, shorter ones. This vanishing act is a telltale sign of the Lyman break, a sharp cutoff in the spectrum caused by the absorption of ultraviolet light by neutral hydrogen, prevalent in the early universe. As redshift increases, the Lyman break moves into redder wavelengths, giving astronomers a way to identify candidates for truly ancient galaxies. Bangjeng Tom Sun, a doctoral student and one of the study's lead authors, explains that this dropout method is the foundation for pinpointing high redshift galaxies. If an object is visible in the red and infrared images, but missing from the blue, it's a strong candidate for being from the early universe. But with Webb's unprecedented sensitivity, the team found not just a few, but 300 such bright dropouts, far more than expected. Once these candidates were flagged, the next challenge was to estimate their distances and characteristics. Typically, astronomers would use spectroscopy, spreading the light from each object into its component colors to reveal unique fingerprints, signatures that can confirm age, composition, and crucially, redshift. But with hundreds of candidates and limited telescope time, the team turned to an alternative: spectral energy distribution fitting. This technique compares the observed brightness of each object across multiple wavelengths to models of galaxy light, providing estimates of their redshift, mass, and age. With this approach, the researchers built a compelling case. Many of these objects likely reside at extremely high redshifts, placing them tantalizingly close to the era when galaxies first took shape. If even a fraction of these candidates are confirmed, it would suggest that the early universe was home to far more bright, massive galaxies than our models predict. This, in turn, would pose a profound challenge to our understanding of galaxy formation. According to current theories, the first galaxies grew slowly, assembling from smaller building blocks over hundreds of millions of years. The discovery of so many luminous, mature galaxies at such an early stage hints at a universe that was more efficient and more mysterious than we ever imagined. Yet, caution is essential. In the past, astronomers have encountered objects that seemed like early galaxies, only to discover they were something else entirely, perhaps rare types of stars or other cosmic phenomena that mimic the appearance of distant galaxies. That's why the final word will come from spectroscopy, the gold standard for cosmic identification. Already, at least one of the objects identified in this study has been confirmed as an ancient galaxy via spectroscopic analysis, but hundreds more remain to be examined. As the Webb telescope continues its mission, astronomers are preparing for the next phase, using its powerful spectrographs to unlock the secrets of these mysterious objects, one by one. If these are truly early galaxies, their discovery will reshape our view of the universe's first billion years. And if they aren't, they may point to new phenomena altogether, unknown chapters in the story of the cosmos, waiting to be written. The search for answers is well underway, propelled by teamwork, advanced technology, and a sense of cosmic curiosity. As we push the boundaries of how far we can see and how much we can know, discoveries like these remind us that the universe holds surprises beyond anything we've yet imagined. With the identification of these 300 unusually bright objects, the James Webb Space Telescope has propelled us to the very edge of what is currently knowable about our universe's infancy. Each candidate, selected through the dropout technique and characterized using spectral energy distribution fitting, is a potential window into the universe as it was just a few 100 million years after the Big Bang. The brightness of these objects defies expectations, challenging established models that predicted far fewer and much dimmer galaxies at such early times. But what's truly remarkable is the process that brings us these discoveries. The dropout technique, which isolates high redshift objects by looking for their disappearance in certain wavelengths, is a product of decades of astronomical innovation. By harnessing the power of JWST's near-infrared camera and mid-infrared instrument, astronomers are able to peer further back in time than ever before. The faint glow detected in these images is not just light, it is a message sent across billions of years, carrying secrets from an era when the first galaxies were assembling from primordial gas. Of course, identifying a candidate galaxy is only the beginning. Estimating its distance and intrinsic properties relies on careful modeling. Astronomers fit the spectral energy distribution of each object to determine its redshift and to infer details like mass, age, and star formation activity. But even the best models have their limitations. That is why the final word comes from spectroscopy. Spectroscopy acts as a cosmic fingerprinting tool, breaking the light from each object into its constituent wavelengths and revealing telltale features, such as the Lyman alpha break, that confirm whether we are truly seeing a galaxy from the dawn of time. So far, at least one of the objects in this sample has been spectroscopically confirmed as an early galaxy, but the rest await their turn under the microscope of JWST's powerful spectrographs. If even a handful of these candidates are verified as being from the early universe, the implications will be profound. Current models of galaxy formation may need to be revised to account for more rapid or more efficient assembly of matter in the primordial cosmos. The presence of so many bright, massive galaxies at such a young age would suggest that the processes that drive star and galaxy formation were already in full swing just a few 100 million years after the Big Bang. Alternatively, if some of these objects turn out not to be galaxies at all, but something entirely new, perhaps previously unrecognized types of stellar clusters or even exotic objects, then we are faced with the